Okay.
Let's go ahead.
Okay. So I wanted to give a talk in a kind of a level where it shows that research is accessible at any level, and some of these slides I will go over would be um, not questions that will be asked at a research level, but questions that were asked in the progress of proving something at the research level. So a lot of these questions I had to solve for my papers. So just give you an idea that research can be accessible and you can actually do research starting at basically any level you feel like if you find a nice question and have good guidance and mentorship to help you. So if there's a question that you would like to answer yourself, I will pose them to the audience, then please interrupt and give the answer if you have an idea. Okay, so I went over some of these things last month, but I'd like to go over it again. The first slide, ooh, I don't have a title even. Ugh, okay, not good. But the first slide starts with this group. This is called the absolute Galois group of Q. This is the algebraic closure of Q, and I will describe it now. Well, the whole reason I'm talking about this is arithmetic geometry is essentially applying number theory and group theory to questions that you would encounter in algebraic geometry. So, for example, an elliptic curve is a curve. It's a geometric object. But a lot of questions we can ask about elliptic curves concern number theoretic flavor, like questions about primes, reduction, things like that. And the most important thing is this Galois group. This is the most important object for arithmetic geometers. This GQ, I'll just call the absolute Galois group of Q, is a group of automorphisms of the algebraic closure of Q that fix Q, Q being the set of rational numbers. And the most interesting thing about this group, in my opinion, is it's extremely difficult to study straightforward. Um, it's an uncountable set, of course, and you can think about why it's uncountable, but we can only really write down two distinct elements, at least so far as I know. Does anybody know two distinct elements of this group? I'll give you one of them. How about the identity? Does anybody have an opinion for another element?
Yeah, definitely there should be infinite many elements for sure. If this is finite, so this is very surprising and nothing to study.
But what about a second element? What about, can you give me an element? Can you give me an automorphism of Q bar that fixes Q? What about complex conjugation? So complex conjugation and the identity is the only really two elements, the two automorphisms of Q bar that fix Q that we know of. But sometimes in math, we do things in a non-direct way. We can study this GQ not exactly by its automorphisms, but how it behaves on elliptic curves through this Galois representations and a nice group action on elliptic curves that we will study soon. But first, some background again on elliptic curves. I went over these topics last month, but we can
So,
refresh.
Karin, so
Yep.
if you don't mind, so for each of the slide, may I just stop you and ask some like a
Mhm.
questions? So then if
Yeah.
you allow it, then you might not be able to finish the slide you planned. Is it okay with you?
No problem. No problem. Go
Yeah.
right ahead.
Okay, so I just wanna just simply just stop for each of the slide and just share my very like a stupid and very like the naive like the imagination about the beyond and behind like the structure. So as I said last time in my talk, when I think about Q, just a Q. So
Yeah.
Q is the just is coming from Z, just the set of the integers. And from algebraic geometry point of view, Z is resembles the polynomial, basically polynomial ring. So it's we start from like the Z of X. Sorry, just a Z. And then if we just make the fractional like the field, then we make it to be Q. So the exact like the analog is we are looking at C of X. C of X just a one variable like the polynomial like the like the functions, and if we just also take the fractional like the field, it becomes the so-called the rational functions as a field or the just a metamorphic function in complex. analysis. And because the goal of like this study is toward algebra, basically, so it makes sense of taking the algebraic closure. So otherwise, what can you do? But the algebraic closure by its like the nature, so it's also closely related to studying the zero of the polynomial. So it's all about like understanding certain like the structure from the like a polynomial ring in some sense. And then what is the Galois group? So of course we know the definition of Galois group, like the separable and also the some like the condition for the field extension for sure. But it's the basically just a group. But so in my like the way of thinking is the following. So it could be a little bit abstract, but if you have different like the opinion or if you want to share your own like the ideas, let me know. So for me, Q is the set of the functions. Set of the functions is coming from Z. So it's coming from the rational functions. We start from C of X and we take the fractional field. It is like the C round of X. So we start from Z, we take the fractional field, it is Q. So when we declare the Q already, so we start from certain topological space. In algebraic geometry, this is called so-called Zariski like the topology. So behind. So there's a certain topological space, and we just collect the reasonable functions that we do like called by the rational functions. And this Q is just such a like the case. So we have a certain topological space, and then we collect some of the functions so that we make it so-called a function field. And on the function field, we just take a algebraic closure, and then we just look at the like a Galois like the Galois group there. So it's kind of the so this what is the purpose of this Galois group in like a geometric perspective? So we'd like to understand the like the geometric like the structure of the underlying topological space. Or I can fancily say we'd like to study the symmetry of the underlying topological space. And in order to know it, we are looking at the Galois group. But this is now the arithmetic like the point of view that we just remove the like a C bracket of X and the like the manifold functions. We just now look at Q and Q bar and Galois group so that we have just a kind of the analog. But in algebraic geometry, we expect some analog should be quite like the nature, and still we can apply some of the like the intuition from what I explained. So that's kind of I'd like to share. So it's just a heuristic. It's just a dummy, but yeah.
Nice.
Okay.
I love it. I love to hear it. Yeah. Should I continue?
Yeah, yeah, sure.
Okay. So if no other questions or comments, let's move on to the second slide. Okay, so the I guess second most important object for arithmetic geometers, in my opinion, are elliptic curves defined over the rationals. A rational elliptic curve is a smooth projective curve over the rationals that can be described by a Weierstrass equation of this form here. A and B are rational numbers, and we want this discriminant for a cubed plus 27b squared to not equal 0. If it is 0, there is a cusp, and that is no longer smooth. That's why I said smooth, and that's why I want this condition. So points on E, I'm going to write in this homogeneous form with these square brackets. They are of the form ABC, where A, B, and C are elements of the algebraic closure of Q, but I don't want all of them to equal 0. And the last comment I'll make is two such points on E will be equal if and only if they're the same, up to a scalar multiple of lambda. Lambda is some element in the algebraic closure of Q. If you plug in Z to be 0, the left side will equal 0, and everything on the right side will equal 0 except x cubed. So x cubed and Z will both be 0, meaning x and Z are both 0. That means y is not 0. So you have something of the form 0, y, 0, y is not 0. And so after you reduce by a scalar factor, y can just be said to be 1. So let's forget the homogeneous form from now on. Let's dehomogenize for the rest of this talk. Elliptic curves defined over the rationals are of the form y squared equals x cubed plus ax plus b. A and b, again, are rational numbers that satisfy this smoothness discriminant condition. The only point I would miss is this point O at infinity. So just so that you have it in the back of your mind, there's nothing wrong with writing it this way. And from now on, we will forget square brackets. We will write round brackets. Points on the elliptic curve E will be of the form AB. AB are in the algebraic closure of Q satisfying y squared equals x cubed plus capital AX plus capital B. Okay. Any comments, questions, suggestions?
Yeah, so let me try to interrupt for each of the slides for today, no matter what. So,
Very nice.
so the very difficult question, in my opinion, truth be told, is the why we all of a sudden consider this very highly non-trivial form of the certain equation. So, in from like the middle school and the high school, like the mathematics, we like the quadratic, like the polynomials, and even for the cubic one, we know, or we could apply just taking derivatives so that we were able to drive draw the like the graph. Other than that, actually, we never ever look at the cubic like the polynomial before, and all of a sudden we just look at this quite complicated like the form of the elliptic curves, and it's everyone says this is super highly important in number theory, and elliptic curve itself is super important like the topic in mathematics. I completely agree with it because so many like the important like the works are coming from this like the business for sure. But what's the point of looking at this guy? So here is my very like also like the naive like the way to think from the algebraic point of view first. So for algebraic, sorry, for abstract algebra. So when I teach abstract algebra as an instructor, I always put emphasis to students that you first should look at the very like the silly but very so-called penetrating example, very concrete, but the example itself already contains all necessary like, the intuition and how to take the abstraction. So that there must be the first like the non-trivial but important like a concrete example first, and by observing some important like the perspective, so that we are able to generalize, abstractize that like the concept mathematically speaking, then we know once we get that abstraction, then it actually covers implemented as non-trivial examples. That's the benefit of the looking at the abstract algebra. That's the way I learn algebra. So for that perspective, I think we need to look at the torus. Torus, what I just meant is really like the silly like the donuts. Donuts is what is donuts? S1 cross S1. We have one loop, another loop, so that we have the S1 cross S1, and we know S1 is the subset inside of the C1 complex plane. So S1 cross S1 is the subset inside of C2 in C2. So everything is written in terms of the complex coordinate is okay. So now we have a certain reasonable topological space, S1 cross S1. Then if we just look at the perspective of the function space, so function space just means we just collect all those rational functions, which is a field. So, and it is known. So, for example, if you think about this like a so-called S2, just a two-dimensional sphere, two-dimensional sphere. So, or like the collection of the rational functions is nothing but the so-called C of X. Let me write down on the chat screen. So, if you look at S2, or you can say this is CP1. So, its function space, function field becomes C round of X. That means the meromorphic function is generated by only one variable. And from this like a point of view, if you look at the torus T, written by S1 cross S1, then the function field it is known from biostress that it is known as a C generated with P and P prime. Here P is biostress P function. Let me write it. This is very important classical like the historical like the remark that the torus whose function field is generated by two elements given by p by the p function and also p prime. So if you look at the like the max exchange like website, you can see concrete like the form of the bias p function, which whose like the pole has a degree 2. So therefore the p prime is a like a pole of degree 3. And you can also find the way to embed from the torus to the elliptic curve. So this like a embedding is described in terms of P and P prime. And because this is embedding, one can write down the polynomial relation that becomes the Weierstrass equation that this like the elliptic curve is described. So the reality of this small x and small y are coming from P and P prime. And this form you wrote, as you explained, is the so-called homogeneous like the form. So here was the like the reality what was happening. So we start from the torus inside of C2, but C2 is the subset inside CP2. So that we just found the way to embed from torus to the CP2 by using the bias P, like the bias P function and its derivative. Then it describes this like bias relation first. Then the torus is characterized in terms of the lattice group. That information is recorded on the coefficient capital A and capital B here. So this capital A and capital B completely determines the lattice structure of the torus. And now once we have this equation already possess all necessary information of the torus, so that we now want to give up the complex factor numbers. So originally we start from the complex pair x comma y satisfying the biases equation. But once we obtain this equation, then we just want to plug in the rational values. Why not? But we just want to make sense of it so that we still keep the biases equation. Then just we'd like to plug in x and y to be just either the rational or coming from the algebraic closure of the rational. Now it starts from the arithmetic geometry. And once we take the homogeneous like the form, so the whole point of this like this slide in the geometric point of view is we just embed the torus to the CP2 projective space. So that's why we take this like the homogeneous coordinate, still the projective space over the like the different view. And then now we can keep all like the algebra like the information so that we can just play with the algebra. So that's like the point I wanna add.
Very nice. If nothing else, I will move
To add
on.
another point. So Tony just gave a very important, like a geometric perspective or a geometrist point of view, why torus is important. And of course, yes, that's how we understand all these like from this elliptic curve to the torus and torus to the function field. That's of course a very important observation. Number theorist observation is, of course, they're real interested in the torus, but the reason why they're interested in the genus one cases, genus zero cases, well, there's only like a line or a conic for that one. First of all, number theorists are really interested in finding out the integer solution or rational solutions to a given equation. Of course, this is one equation here, projective cases, then of course we're interested in the integer solutions. And this like a behavior or the distribution of this rational solution of an equation is solely determined by the genus. So if it is a genus zero case, then either it has no rational solutions at all or infinitely many rational solutions. However, they do not really have any kind of particular interest in group theoretic like a structure. It doesn't really have any algebra, just like, yeah, there are many solutions, but we can't find them all. But yeah, that's all. However, for genus 2 or higher, there are not infinitely many. I forgot the name of the theorem. It's a very important theorem, but there are
Parting
not.
theorem. I think you're talking about parting
Yes,
theorem.
exactly. Falking's theorem. And there are not infinitely many rational solutions. And even though there are only finitely many, we don't have any particular group structures about now. And so finding out these solutions are extremely hard. There are many tools been invented to like scavenge these rational points. For example, Shabati's method is used to find it like a hyperelliptic curves and stuff. For genus one case, however, it's a very particular gray area, but at the same time, very much well known. There can be no rational points, finitely many rational points, infinitely many rational points, but no matter which case is, they form a group. So the good thing about the group structure is once you find the generators of this group, then we can actually find all the rational points of the elliptic curves. And that's one reason why I'm really interested in the Galois representation because it really helps us to how to like the some indirect way of understanding the rational points group structures and also finding out the generators and all these kind of stuff. So I think that's another important like a pillar of why mathematicians why are like arithmetic geometers are interested in the elliptic curves in particular. Yes, geometrically it's a torus. We have a lot of things known about the torus thanks to Weierstrass P function and the function field. But also another reason for this particular case, they form a group structures and finding out this rational points as very like a promising ways and promising methods.
Yeah, so I will also talk about group theoretic ways, which will also give um, intuition why we care so much about elliptic curves. So if no other comments, suggestions, or questions, let's move on to slide 3. Okay. So again, elliptic curves, like many mentioned before, have a abelian group structure. I went over the process earlier, last month. I mean, we'll go over it again very quickly. So if there are 2 points, P and Q, on an elliptic curve, the way to add them with the group theoretic binary operation is, say you want to draw a chord, a secant line. through P and Q. That line hits the elliptic curve at three different points, P, Q, and this third point here. This is not what P plus Q is. What then you do is you draw a vertical line through the elliptic curve that hits this third point. The point you get that the point on the vertical line and the elliptic curve other than this point is what P plus Q is. So that's how you add two non-equal points on an elliptic curve together using the group theory binary operation. On the other hand, let's say you want to add a point to itself, which is also extremely important. Say you have the point Q, you want to add Q to itself. Instead of drawing a secant line, of course, draw the tangent line. So this tangent line hits the elliptic curve at Q and another point here. Again, you use the vertical line operation, and then this vertical line hits the elliptic curve at this point here and another point here. This is what 2Q is. And with those ideas in mind, you have a group theoretic binary operation.
Yeah. So let me just interrupt this part. So the part that I really didn't get the ingenious inspiration from this very important the picture is what the heck the previous generation of the mathematician came up with this crazy like the abelian group operation. This seems just a right like a nerd. So what the heck was really going on behind? That was what I was thinking before. Here's my like the current like the best possible like the interpretation to digest in my own way. So what is the reality elliptic curve torus? And the torus is written in terms of the bias equation. I'm just talking about the just complex like the x and y satisfying the bias equation. Then the picture we are saying this as a curve is that we just look at the so-called the real part. So x and y, each of x and y are complex like the values. So it's actually the four-dimensional information. There are four independent variables, but we just project down to the real part for each of the complex like the numbers x and y. So that's what it becomes like the this type of the curve which looks completely disconnected. So this is what I'm imagining. You have a torus. You have a torus. Actually, this is sit inside of the either the C2 or CP2, and we just project down to the rear part, and that rear part, like the trajectory locus, looks like this type of the curve. Then if we think about the torus, torus is S1 cross S1. What is S1? S1 is the so-called group. So e to the IT, we know this is very like the continuous like the group. Then what is S1 cross S1? Product group. So that if you look at the torus, this is clearly the abelian group for sure. Then if we just, because the embedding preserve all necessary information, including algebraic information as well, so that as long as S1 cross S1 torus itself is the abelian group, then the elliptic curve equation possesses the same structure as well, then we are able to following the like the trajectory from from S1 cross S1, just to describe the corresponding like the binary operation like the trajectory, then if you just take that as a projection, that should be this one, should be the result. So that's what I try to imagine how man or cook up with this like the genius like the inspiration. So this is my own like the interpretation. That's what I want to say.
That's truly amazing. They came up with this 200 years ago. Really amazing. All right, moving on. Okay, so just to give you notation, so for an elliptic curve E, I'm going to designate the group operation on points PQ on E as just P plus Q with this O plus LaTeX notation. And the inverse I'll write with the typical negative. So you want to think about, because it's an abelian group operation, we use addition, okay? And multiplication by an integer is important. So if you have a point P on E and you have an integer n, and you want to multiply P by itself n different times, if n is positive, I'll just say n times P is just the compact multiplication of how to write P plus P plus P n different times. We'll write using square brackets. On the other hand, what if I want to add P to itself a negative amount of times? That's the same thing as adding negative P to itself. That same number of times, but take the positive amount. So negative n times P is adding negative P to itself n different times. And of course, 0 times P, I'll just say is what we want to designate as a zero number, 0 point on the elliptic curve. That is going to be O, the point at infinity, 0, 1, 0. All right.
Yeah, my turn to interrupt. We do not need to like to open this like the file here, but I want to emphasize like this like the abelian group like the structure. Indeed, this is really coming from the line integral. Seriously. So if you have a, like the so I'd like to reinterpret everything from the complex like the torus point of view. So if you start from the like the torus, then there are so-called two homological cycle, which is not constructible for sure. Then for each of the like the loop, I mean the cycle, then we are able to extract so-called corresponding differential one form, one form, one form. And if we take the complexify with this real part, this imaginary part, this is called the canonical one form. Even you look at the Silverman's like the textbook, the canonical like the one form is the way to describe so-called the structural shape as an identity element and so on and so on. So so that so if we have like the differential warm form, then by just taking the line integral, you are able to actually recover the torus. And this is actually coming from the following that interpretation from Linus. You can look at so how do we use the short sequence and the homological like the algebraic interpretation of the line integral in a way that this is indeed coming from the so-called zero divisor, quotient out by so-called principal divisor. So this is also very surprising fact, and this is actually birth of the abstract algebraic geometry in my understanding that so we start from the complex torus and take just a line integral, and then that can be conformed as a so-called a Picard group. Picard group is just a zero, like the collection of zero divisor, quotient out by like for example, like the divisor. Then it just became these types of the completely abstract algebraic like the object. But the way to like to make this transition is really like a so from like a chemistry point of view, it's completely like the different it looks like, but it's indeed coming from calculus. That's what I want to put emphasis to the algebra like the people that this is not coming from the like the genius inspiration. In my opinion, this is indeed coming from the line integral. And you can just look at the detail from my note. I actually teach this in my like the YouTube channel for the like the students. This is very important like, the fact. Yeah, that's one comment I'd like to add. Yeah, thanks.
All right. So if everybody's comfortable with the algebraic and group theoretic notation, let's move on. This is, to me, an amazing part of the algebraic properties of elliptic curves. Yes, abelian group structure is amazing, but also this group GQ that I defined above earlier acts on E. So if you have an elliptic curve, you have a point P, let's say Px is the x coordinate and Py is the y coordinate. This group action, if you take a Galois automorphism, meaning an automorphism of Q bar that fixes Q, an element of GQ, you have a very natural, obvious group action, sigma times P. You just take the Galois automorphism on the coordinates. And from there, you have a group action of GQ on E. So that's nice. That's very nice. One of the most interesting things out of that is, we'll say a point P, A, B on E is rational if A, B are rational numbers. And we'll denote the set of all rational points on E by E of Q. We're not going to study too much about this E of Q today. I have a question for the audience. A point P on E is rational, meaning points of the form AB, A and B are both rational numbers, if and only if sigma of P equals what? What will sigma of P equal if P is rational? So please interrupt if you want to contribute.
So from the like the intuition, so from the Galois group, from the like the solve field, we know we need to fix the like the solve field. That might be the correct answer. I mean, at least the correct like the direction.
So fixing means equal. So sigma of P must equal P for all sigma in the Galois group, in the absolute Galois group of Q. So P, a point P and E is rational if and only if nothing changes when you evaluate a Galois automorphism on it. So take 2 points, P and Q on E. Another amazing thing is that if you take the Galois automorphism on P plus Q, it's exactly the same thing as taking the Galois automorphism of P and taking the Galois automorphism on Q and just adding them together. This commutativity of this operations gives you so much richness in the algebraic properties. Using these two lines here, you prove that E of Q is a group. The set of rational points on an elliptic curve has the structure of an abelian group. And that's really, really amazing. Okay, thanks.
Yeah, so here is not, I don't want to share my inspiration. In a sense, I don't know anything here, but for me, this is surprising in a sense that over complex like the field, so everything is indeed like the purely geometric. So I can just think about like the continuous like the torus, and then every like the interpretation should be just generated from like this interpretation. But now we really look at everything over like a cube, and this like the structure is just amazing. I still do not know why this really happens. In a sense that if the like the biostat equation is given, for example, on the like the finite field, then the reality is with the biostat equation, this is a finite set. So even equipped with the same equation, I don't really like the can easily accept that it really enjoys the fruitful like the algebra like the structure, but at least like these slides shows that we can really now give up the like the complex like the field interpretation. Everything is over Q, and still we can just look at the algebraic structure that does not lose any information. So for me, it's kind of amazing. I still do not know why Q behaves something so nice. So for me, what is Q? We look at just N piano like the axiom, and then Z, okay, group like abelian group. I'm okay with it. So fractional field Q, yeah, it's intuitive. That's what I thought. But why it does it preserve this like the nice like the structure? I have no idea. So I'm actually wondering. Yeah, that's what I want to say.
Okay, let's move on if no other contribution from the audience. All right. So this is also a very important property of elliptic curves. So if E is an elliptic curve over the rationals and N is a positive integer, the subgroup of E of elements of order dividing N, not just equal to N, dividing N is denoted E bracket N. And I'll call these the N torsion points. Meaning that if you twist it N times, you'll get to 0. Moreover, we know the group theoretic structure of E bracket N. It's the same thing as Z mod NZ squared. This is extremely, extremely important. Just the fact that we know what E bracket N is, and E bracket N is, and the fact that it's the same all the time, it's really amazing. So the next thing is the whole reason why this Galois automorphisms, this Galois group is so important. So sorry, let me just say very quickly. This E bracket N group, let me kind of give you an idea of how I think about it. So you always will be able to find 2 points, P and Q in E, both of which have order N. And another important thing is the group that it generates. So this Langle-Wrangles, these angled brackets, their intersection will be trivial. So you can always find P and Q whose orders are both equal to N, and they intersect trivially. This PQ will serve as a basis of E bracket N. And using this idea was very important from my research. It always is. So for each Galois automorphism, because we have this commutativity, sigma of E bracket N will always equal just E bracket N. That doesn't mean every point is fixed, but you can move it around in a group, but you will never break out of this group. Sigma of E bracket N will always equal E bracket N. So not only is sigma an automorphism of Q bar, actually, now it's also an automorphism on E bracket N. So if we take this idea, why not make a Galois representation out of it? So what I'm trying to say is you have a basis of E bracket N. You can always find the basis of E bracket N. Fine. E bracket N will always look like this. So what does the automorphism group of E bracket N look like? It will look exactly like the automorphism group of Z mod NZ squared. But why are we going to suffer so much by thinking about group theory? We already have so much of this algebra done for us. It's just a set of 2 by 2 invertible matrices with Z mod n Z coefficients. And so if we take the all the Galois automorphisms on E bracket n, we can make a mod n Galois representation. You have this map here. You take any Galois automorphism on Q bar, and you just treat it as the same exact thing, but now as a Galois automorphism on E bracket n. Or what about a better way of thinking about it? It's just a matrix. It's just a matrix. If you look at it, reducing modulo n on elliptic curves. So this, all these elements on, where did I write it? On this GQ, you can view it as 2 by 2 invertible matrices when you look at it as the viewpoint on elliptic curves. And this is really amazing, and it's really helpful for my research. Okay.
So before I interrupt, so it seems Nara has one question. So no, so she says just P, but yeah. So if Nara
No,
says,
I have many questions that I cannot
Oh,
think of. But no, I just don't have like a lot of understanding of Galois representation, so that I haven't studied yet. But yeah, so far it's interesting.
it's not a bad thing. Just think of it this way. And now just black box. Black box meaning it's just matrices. Just think about matrices. Matrix, matrix, matrix. That's it.
so also let me also share my other stupid like the inspiration here. So what was
Only if you stop calling it stupid. I love your interpretations. I'm learning
yeah.
a lot. So
I'm just
very
stupid,
interesting.
so I just want to say, but I want to put emphasis. This is just like a stupidity. So why this actually really holds? So beyond like this algebra, like the rigorously. So what is the elliptic curve? So it's coming from S1 cross S1. So S1 is a continuous group, but now we'd like to look at the discrete subgroup. So S1 cycle is it resembles a cycle group. So therefore, so as long as we just require the condition that the P like the bracket intersect Q bracket is just kind of empty, so it kind of just makes so that we have one cycle, another cycle that behaves sort of independently. Then from the like the algebra like the compatibility condition, it just has the same order of the generator. So in that sense, it kind of makes sense for this fact. Of course, the proving this rigorously is completely different like the issue. I know it, but kind of makes sense as long as it's coming from the discrete like the cyclic subgroup coming from S1 cross S1. That's one thing I want to say. And what is the like the meaning of the like the Galois group? So Galois group is we just look at the subfield and we have an extension field and we have the our automorphisms fix this like the subfield. That's the definition. But what does that mean? So here's my way of thinking, and hopefully this actually works many times. So if you have a, like a torus, so I share some of the note last time that if you just take the like so-called the 180 like the degree like the rotation taking quotient that becomes the two-dimensional like the sphere. Two-dimensional sphere is coming from the like, so-called G sub C here. So we are replacing just the Q by C. So it is kind of so we just fix. So we have a torus. We have a torus. We rotate torus this way. That makes the two-dimensional like the sphere. Two-dimensional sphere is a base space and the top of it, it has a like we have a, like a torus, which is an elliptic curve. So the like the way to think this Galois like the group in my perspective. So if we want to look at the from the complex like torus from the one complex torus to the another, or elliptic curve to the elliptic curve, then it also descends to the like the two-dimensional sphere, or we can call it by the rational like the curve. Then what this Galois group is really doing is that so we'd like to move from the elliptic curve element to the another like the elliptic curve like the element with fixing this like the S2. And if we try to do it, so still, even we change the elements, still it fixes the same like the elliptic curve. That's the meaning of the rho of this sigma. And it completely makes sense of, so if you start from the automorphism from the elliptic curve to the another, so we'd like to discover everything in terms of this like a discrete, like the subgroup information. That's, so I think Karen tells this is a Galois representation in this context. That's kind of my imagination.
Thanks so much. Okay, let's move on. Let's move on. Again, so the theory is important, but for me, problem solving is the more important. So, like the typical, like that question, I forget who said it. I think Raymond Dyson said there are birds and there are toads. In math, birds like to view things many different fields and then gluing them together. I'm a toad who likes to do a lot of questions in a specific field, and I like to really deeply learn one field. And we'll try and do these questions. We'll try and solve exercises about these mod and Galois representations and show you really it's um, very, very accessible. Okay, so for example, let's say E is an elliptic curve and N is a positive integer. So suppose this is an element of the image of the mod and Galois representation. So let me go back. So this map is very important. We care actually more about the image. We don't care really how the map works. We care more about the image because it's almost impossible to know how the map works because, like I said, we only know two elements really of the Galois automorphism of Q. Sorry, Q bar. So consider, let's say, I give you such a matrix. A, B, C, D is an element of the image of the mod and Galois representation on GQ. Let's say A, B, C, D are integers, and then this is an invertible matrix modulo n. Okay, so that means I can find you elements Pn and, Qn on E of order n. That's why I wrote n as a subscript. And they intersect trivially. There's only one element inside both those groups. And there's a Galois automorphism on GQ such that if you evaluate on Pn, you get this vertical left column. And if you evaluate on Qn, you get this. Oh no, I wrote it. Oh no, I should have wrote this. B should be C. This should be a B. Sorry, this B should be a C, and this C should be a B. I'm sorry, my mistake. I went over these. I knew I still had some typos and mistakes, but sorry. So don't think of it this way. Think of the transpose: APN plus CQN, BPN plus BQN. I'm sorry. Okay, so let's stop here. Any contribution from the audience?
So for this slide, I wanna say, indeed, really sorry, actually stupid. So I think this is magic in a sense that so we reduce the information in terms of 2 by 2 matrices that we can definitely handle very concretely. That's one thing. And moreover, from the previous slide, so as you said, all these information is coming from the set inside of the like z sub n, like the square. It's just a so our reality is really like just a simple like the cyclical information already. So and this is very like the computable. So this like the framework itself is very amazing. That's what I want to say. I was wondering who first like thought about this kind of the like the framework. So once this one is established, so one can just play with just simple algebra.
Maybe like Fermat, maybe people around his time. 1800s, I think. Maybe John has a better opinion about the history, but I don't. Okay. Okay, let's move on. Okay, there's the first exercise. Let E be a rational elliptic curve and N be a positive integer. Then we say that E has, oh, oh no, I mixed this up. Okay, one sec. No, no. Oh no. I wrote this at the incorrect. Yeah. Okay. Let's go here first. Let's go here first. Okay. It's exercise 3. I'm sorry. I wrote the exercises in the incorrect order. Let E be an elliptic curve and N be a positive integer, then the determinant map is surjective. Meaning in the image of the mod n Galois representation, you will always find a matrix of determinant D. D is an invertible element modulo n. So let's say you're working over, let's say Z mod 4Z. what are the invertible numbers modulo 4? Of course, you have 1 and you have 3. So let's say I have an elliptic curve. The image of the mod 4 Galois representation will have an element of determinant 1, and it'll have an element of determinant 3. What does this have to do with some question we can give you about elliptic curves? Well, let E be an elliptic curve defined over the rationals and be any positive integer. Suppose that the image of the mod n Galois representation contains every group of determinant 1. Can you tell me what the image of the mod n Galois representation is? So with my research and my work, I give you questions with very little information. So the answer has to be obvious. It has to be. Because otherwise, how could I give you so little information and expect an answer? What is the image of the mod n Galois representation when the image already contains all elements of determinant 1? Maybe somebody contributed with a chat. I have trouble bringing it up. John is correct. John says full group. Why did John say full group? Well, let's go over the answer. Well, let's say D is an invertible element modulo n, then the image of the mod n Galois representation contains an element X of determinant D. John claims that it contains every element of determinant D. Okay, fine. Well, let's say Y is an element of this invertible group of 2 by 2 matrices mod n, has the same determinant as X. They both have determinant D. What is the determinant of X inverse times Y? If determinant of X is D and the determinant of Y is D, then the determinant of X inverse is 1 over D, and the determinant of Y is also D. Fine. So that means X inverse Y is an element of the special linear group. But that's an element, that's a subset of the image of the mod n Galois representation. I told you in the hypothesis, the image of the mod n Galois representation contains the special linear group. But then Y is just X times S, the product of two elements in the image of the mod n Galois representation. So that means John is saying Y being a random element of a random matrix, 2 by 2 matrix, invertible matrix over Z mod NZ. And now you just showed me that it's the product of two elements in the image of the mod n Galois representations. That means the image of the mod n Galois representation, as John said, is the full group of 2 by 2 invertible matrices over Z mod NZ. This comes up in a very important question called Serre's uniformity question, where you break down groups that are maximally possible that an elliptic curve can have. One such case is the elliptic curves will contain SL2 of Z mod NZ, and therefore you know the image is the whole group. Okay. Any contribution from the audience?
So, what is the
Any other contribution from the audience?
I just want one silly question here. So, in your the second line, so what is the meaning of the determinant is surjective? I mean, I'm talking about not example. I mean talking about yeah.
So for every invertible element modulo n, the image of the mod n Galois representation will contain a matrix of determinant D. It will I'm sorry.
Yeah,
This E should be a GQ. I'm sorry. This E should be a GQ. See,
Okay.
another mistake.
I got
This
it.
E should, yeah,
Mm,
my mistake.
thanks.
Okay.
And so is it so I understand the like the logic you explained. So how do we come up with the equality from the like the Galois representation and this like the general linear group? I can got that how one use like the special like the linear like the group here. So is it necessary or just a sufficient to achieve this?
It's equivalent.
I see. So in order to achieve this equality as a conclusion, then okay, so this is a characterization. Got it.
So I'm working on a paper. It shows you how important this is, SL2 as a subset of the image of the mod and Galois representation. This group is extremely hard to work with. So hard. So hard. Okay. Any other questions or contributions?
I can add a quick comment. So, by the way, this is actually the fact that the determinant group is surjective comes from the known fact from the values pairing. And values pairing is an extremely important way to understand this. But basically, it means if you have an elliptic curve and you can consider the dual of the elliptic curve, but actually this argument works for not only the elliptic curve, but the higher general case. If you consider elliptic curve pairing with the dual of it, however, for the elliptic curve, the dual of the elliptic curve is itself. So particularly for the elliptic curve, you can consider a map. You can make a pairing from the elliptic curve times dual to all the root of unity, and that gives why this determinant map is surjective. So this also gives us a very important idea that there should be a lower bound of the size of the images of the Galois representation model, and because it should contains this full determinant, so it should be at least a phi of n. It gives you a lower bound, but also we are interested in like how many different possibilities of this the mod n Galois representation are. We know the lower bound, but most of the cases we don't know any. Of course, the trivial upper bound is the full group, but many cases we have no idea. But we have some like a known fact about if n is larger than a certain number, then this Galois representation group must be certain form, of course. And I think Garen will be talking about more details about it. But this is, I think, how should I put it, the most elementary and the primary steps to understand the Galois representation model and image should be at least containing the full determinants group.
Okay, everybody. I know I'm running out of time, but please allow me to go over two more examples. So I'll go back to that first example I accidentally went over. Okay, so let E be an elliptic curve over the rationals and N to be a positive integer. We'll say E has full N torsion, meaning all those points are rational. All the N torsion points are rational if E bracket N is rational. So full N torsion defined over the rationals means all elements of E bracket N are rational. E has full N torsion if and only if what is the most obvious thing that the image of the Galois group has to be? It has to be trivial. That's the only way all points of order N are rational. Now my next question is, let N be any integer greater than or equal to 3. Prove to me that E does not have full N torsion. And please remember the property I said about the surjectivity of the determinant map that we went over earlier. Why doesn't E have full N torsion if N is an integer greater than or equal to 3? The surjectivity of the determinant map will play a big part in this. Well, let's say it does have full N torsion incorrectly. Then the image of the mod N Galois representation will be equal to just the trivial group. But here we have a problem. 1 and N minus 1 will both be invertible elements modulo N. But there will be no matrix of determinant N minus 1 in the image of the mod N Galois representation. That's bad. That would break the property that the image of the mod N Galois representation has a matrix of each possible determinant. I have another question. What about N equals 1 or N equals 2? Could you have full 1 torsion? Yes, of course, you could have full 1 torsion. The only point of size of order 1 is the 0 point. Of course, that's rational. Can you have full 2 torsion? Yes, you could have full 2 torsion. We'll go over some examples in the maybe next month. But you can have full 1 torsion, you can have full 2 torsion, you can't have full 3 torsion or anything bigger because the determinant is not, the image of the mod and Galois representation does not have a matrix for every possible determinant. That's not good. All right. Any other questions, suggestions, comments? Let's move on to the final question for today. Let's say E is an elliptic curve defined with the rationals such that the image of the mod 2 Galois representation is this group. I listed off every element of the group. You have 2 elements, 1, 0, 0, 1, and 0, 1, 1, 0. How many rational points are there on E of order 2? It's kind of a trick question because those who have seen elliptic curves and the image of the mod 2 Galois representation of elliptic curve don't really like to see it in this form. And I'll show you a little bit later why. So there's it's kind of an involved question. So I'll walk through it with you. Just give you one more minute to kind of think, what could it possibly be? So before we actually give you the answer, what are the possibilities, like the naive possibilities? So remember, E bracket N is Z mod NZ cross Z mod NZ. So in this case, I'm focusing on 2, N equals 2. So E bracket 2 is Z mod 2 cross Z mod 2. So that's 4 elements. In E bracket 2, you have the point of order 1, and you have points of order 2. So there are 3 elements on E of order 2. I didn't tell you which ones are rational or irrational or whatever. It's just 3 of them are of order 2. Fine. Let's say 2 out of the 3 points are rational. Then their sum is another point of order 2, and that would also be rational. So if you have 2 points of order 2 that are rational, then you have a third point of order 2 that is also rational. So the answer can't equal 2. It's either 0, 1, or 3. If all 3 points of order 2 are rational, remember I said that the image of the mod 2 Galois representation would have to be just the identity. But that's not what I have. I told you that the image of the mod 2 Galois representation has 2 points, 1, 0, 0, 1, and 0, 1, 1, 0. It's not just the trivial group. So I eliminated the example of 3. So the answer is either 0 or 1. So if I can give you a rational point, then the answer would be 1. If I could show you that there's no way you can have a rational point, then the answer is 0. I will show you that there is a rational point. Okay, so let's give ourselves points P2 and Q2 on E of order 2, and they intersect trivially, fine. But they have to behave like this group up here. So P2 and Q2 are in such a way where if you have a Galois automorphism, either the Galois automorphism acts like the identity, so it fixes both P and Q, or the Galois automorphism acts like the other element, the other matrix. So instead of mapping P2 to P2, it maps P2 to Q2. Remember that vertical column I was talking about a couple of slides ago where I made the typo. So sigma maps P2 to Q2, and at the same time, sigma maps Q2 to P2 because 0, 1, 1, 0, they're switching, they're swapping with each other. So if sigma acts like the identity, then the identity map clearly fixes P2 plus Q2. But I'm going to show you that the other map also fixes P2 plus Q2. Let's say you have sigma behaves like this matrix, meaning you swap P2 with Q2. You have sigma of P2 plus Q2 is the same as sigma of P2 plus sigma of Q2. I have to swap, so sigma of P2 is the same as Q2, and sigma of Q2 is the same as P2. But because you're in an abelian group, it's the same thing as just P2 plus Q2. So what did I say? I said sigma of P2 plus Q2 is exactly equal to P2 plus Q2, meaning all Galois automorphisms fixed the element P2 plus Q2, meaning P2 plus Q2 is a rational point on E of order 2. The answer is equal to 1. There's a single rational point on E of order 2. This is how you work with Galois representation. You give yourself nice matrices, or close to nice, and then you see how these matrices behave on these points. You see if they swap them, or if they fix them, or they do some other strange behavior. Any questions, comments, suggestions?
So yeah, so I think these are the sort of the foundational observation from the previous slide that you'd like to attack this so-called like the uniformity conjecture. That's what we're thinking.
Yep. I will conclude with the next slide. So this is for those who want to do research. Sometimes equality is too convenient of a property to have. It's best to work with conjugation. So for example, if you are working with a vector space, you have a basis. It might not give you a nice form of the matrix that you want to have. But if you are allowed to use conjugation, then it's much simpler, actually, to do proofs. So the previous example shows that sometimes the structure of E of Q is not very clear by looking at just the image of the mod Galois representation with a strange basis. It's good to pick the right basis on the image of the mod and Galois representation, meaning that if you have two bases, B1 and B2 of E bracket N, the image of the mod n Galois representation with the first basis might look very strange. The image of the mod n Galois representation on the second basis might look nicer. But what I would say is these two are related because the image with one basis is conjugate to the image with the other basis. So if you give yourself a viewpoint of working with conjugation, it's much better than just forcing yourself to do equality. So for example, if you have P2 and Q2, like the previous example, if you use just the basis P2, Q2, let's say you have this image of the mod and Galois representation, you have this group. It's better to put your rational point as one of the elements of the basis. So let's say you have P2 here and P2 plus Q2 on the right side. With this basis, the image of the mod 2 Galois representation is lower triangle. On the other hand, if you put the rational point on the left coordinate or the first basis element, then the image of the mod 2 Galois representation looks like upper triangle. Upper triangular and lower triangular is much easier to work with than this group. But you're not forced to work with any group. You can work with any group you want to, so long as you give yourself conjugation. Conjugation is your friend, and that is what we should conclude with. If you don't have any other contributions or any other questions. So, any contribution from the audience, please.
Yeah, so I'm a little bit surprised. So in my like a very like a bias.
Oh, I'm sorry. Let me interrupt. One
Yeah,
more time. One more time.
sure.
Algebraically, what does this show us? This group, and this group are what? What are these three groups? What property do they share? They conjugate to each other, modulo 2, of course, because they're the same group. Oh, I'm sorry, with different bases. Same exact group, different bases means they're conjugate to each other. That's what linear algebra is all about. Different bases are the same thing. Oh, no, sorry, not the same. They're conjugate. So
I think so. This is not just a comment on last like the two slides, but my just over like the comment. So it could be completely like the bias, but I just still want to say my honest opinion. So basically, so you're like the approach in my like the point of view is so quite like the uses like the group structure to just try to exclude the cases from the logic because we can rely on the group structure. So once we get the Galois representation, then there are just a finite many cases. Then there should be a clever way to exclude to make some like the conclusion there. But I can actually see that these are really all coming from so-called the either the Abel-Jacobi map or the Riemann like the periodic matrix. So from the algebraic geometry point of view, in my personal opinion, this is all coming from line integral, seriously speaking. So and so that's why I was really wondering. So whether or not, so of course this is an arithmetic thing, I completely admit it, but still at the same time, the one of the recent paper I just library found, so he uses also the like the period like the matrix. This is coming from the line integral, seriously. So if you equip with the like the algebraic geometry like a perspective, so I think so it's really coming from just understanding the like the complex like torus. So yeah, there should be way to just reinterpret what you are actually trying to do in my perspective. And it seems like the important like the question I admit it, but it seems like useful to not just take this problem from the classification wise like the approach, but also some like the geometric perspective to like attack such like the problems. So I think yeah, this is something really like a deep like the problem, and I don't personally think so. This can be attacked by the purely group theoretic point of view. So this is not that simple in my opinion. This is not easy. So
it's
yeah,
very deep. Okay, yeah, yeah, very nice. Please send the paper you talked about.
so I post on the like the chat screen. I will like
Oh,
send
very
it
nice,
to you. Yeah.
very nice. Yes, very nice. Okay, so this concludes my talk. Really, Galois representations are a deep field, but it's not difficult to get started, and you can use it a lot for your research. Trust me, it's very useful and accessible, very accessible. So I solved three questions. Three questions. Let me move. Uh, I will continue this next month. I will continue isogenies, and I'll show you question four. Question four was a very interesting application of images of Galois representations that I had to use for my first paper. So, question is, why can't we have such an isogeny graph below over the rationals? If these number threes are replaced with number twos, that's perfectly fine. But if you keep these as degree three, something very, very, very bad happens. And what's the answer? Why can't we have this? I already went over it. I already went over it. I already went over it right here. I already gave you the answer. It's right here. Of course, I have to give you the steps to show you why we can use this, but it's all group theory, something that you've seen before. You just have to apply it to your research, apply it to your questions. So lots of vast questions you can solve using Galois representations, images of Galois representation. Really a very, very nice field. Something probably all arithmetic geometers will have to do in their future. Thank you for everybody's contribution today.
Thanks for the pressure like the lesson I learned a lot. So probably we can just stop the record here today.